So now that you're comfortable with the concept of a limit and some of the definitions associated with limits and continuity of a function, and more importantly, even for us, continuity at a certain point on a function, we're ready to talk about how we actually go about evaluating limits algebraically, keeping in mind that the goal is to use limits as a way for evaluating instantaneous rate of change or slopes of tangent lines. So recall that if a limit exists, okay, a limit as x approaches a of f of x equals something, whatever it is, we'll just call it L, and that something is the same as the y value at that point, then we say that f of x is continuous at that point. So there's no, it's basically a fancy way of saying that there's no breaks in the graph or no holes in the graph at that point. And what that means is that certain limits can be evaluated just by using simple substitution. Let's look at a couple. So the limit as x approaches 2 of x squared minus 3. I've got the graph of x squared minus 3 for you here. And we can see that I've labeled the point where x equals 2. So this limit definitely exists, both from the left and from the right. So from the left, you can see that you get closer and closer to y equals 1. And from the right, you get closer and closer to y equals 1. And we know that that point is continuous. There's no break or hole at that point. So sure enough, it's not surprising that the limit is going to be equal to 1, which is the exact same thing as if you just subbed in x equals 2. And you can do that because there's no breaks there. You can simply sub in x equals 2 and get the limit that way. Okay, you might have wondered earlier why we didn't do stuff like that. Another example is this function right here, which I've also graphed. Now this function isn't continuous, but at 4, okay, that's a continuous point. There's no breaks at that point. Okay, you can see that the limit exists from the left and from the right. Okay, and you can see that not only does the limit exist, but it's the same as what you get if you just used the equation to come up with that value. And so we can do that. And we get 5 over 4 plus 2, which is 5/6. So as h gets closer and closer to 4, 5 divided by h plus 2 gets closer and closer to 5/6. Not a surprise, just like over here. As x gets closer and closer to 2, x squared minus 3 gets closer and closer to 1. And we say that the limit as x approaches 2 is equal to 1. We don't say that this is getting closer to 1. We actually say that it's equal to 1. The limit is equal to 1. So those ones aren't very interesting, but there they are. If at any time, but most of the time, if you're dealing with a limit and you can sub that value in without anything funny going on, then you just go ahead and do it. And that's true for any polynomial, for rational functions, and most algebraic functions. You can just do that. Another example might be if I wanted to know the limit as x approaches 5 of 5x plus x squared. Okay, there is nothing stopping me from just plugging 5 into that, and you would get 50. And that limit is equal to 50. I don't need the graph to know that's going to work. Okay, so another possibility is that a limit might not exist. So you might want to evaluate a limit, and it's possible that there is no answer, that they don't exist. And here's 2 examples of that happens. The limit as x approaches 0 of 1 over x. Obviously, you can't sub in x equals 0 here. You get 1 over 0. Now you might say, well, as x gets closer and closer to 0, this just gets bigger and bigger and bigger. So maybe the limit is just infinity. Can that be the answer? Possibly, but here's the problem. Remember, limits need to be the same from the right and the left. So as x gets closer and closer to 0 from the right, this gets closer to positive infinity, but from the left, when x is less than 0, it gets closer and closer to negative infinity. Just take a look at the graph quickly. Hey, you can see that very clearly in the graph here. Okay, as we approach 0 from the right, we blow up to positive infinity. As we approach 0 from the left, we go to negative infinity. So the right and left sides of the limits aren't the same. So the limit doesn't exist. And we can write something like does not exist or DNE or whatever else we need to. We don't deal with that a lot in this course, but we should understand that it's possible. Now, this one here is a little bit more sneaky. I mean, you can plug in x equals 0 here and you get 0. So you might say, the limit as x approaches 0 of the square root of x is equal to 0. But that limit doesn't exist from the left because you can't go lower than 0. If we can look at that graph, we can see it right there. So like I said, yeah, it gets closer and closer to 0 from the left, but it doesn't exist from the right. So the left and right limits don't exist. So there's no two-sided limit here. So we shouldn't just substitute it in. It's not super important for this class, but we're going to find that when you use your limits to calculate slopes of tangents, you can't actually calculate the slope of the tangent line at 0, 0 here. And we'll get into that later on. So again, this one does not exist either. Okay, and we're not going to worry. I don't want to worry too much about this example. It's really not that big of a deal. Let's get into more interesting stuff. So more interesting limits are those that are called, have what's called an indeterminate form. And these limits are characterized by an inability to substitute a value. It's when you go to substitute your variable and you just get 0 over 0. And we saw that when we were trying to calculate slopes of tangents. Let me bring up an example. I know at one point in time we were trying to calculate a slope of tangent. We got this calculation right here. As h approaches 0, what happens to this right here? And sure enough, if you sub in h equals 0 here, you get the square root of 4, which is 2, subtract 2, which is 0, and a 0 in the denominator, so an indeterminate form. And what we did then is we just subbed in small values of h to see what happened. Obviously, we don't want to do that anymore. Here are some other examples of where that happens. How about the limit as x approaches 3 of x cubed minus x squared minus 6x divided by x minus 3. If you sub in x equals 3, you will get 0 over 0. It's always a good idea to check that. Because if you don't get 0 over 0, it's not an indeterminate form, and you don't need to do anything else. Either it's, you get a value, a number like 5 or 0, or like we did up here in these examples, or you get like 1 over 0, in which case you have to decide if it's going to infinity or not, or whatever else it might be. Okay. So 0 over 0. So what do we do? Well, this one's not too difficult. We can actually solve this one just by simplification. And when I say simplification, I mean we're going to factor and see if something divides out. So there is a common factor of x here. And when I factor the x out, I get x squared, take away x, take away 6, okay, divided by x minus 3. And we can keep going from there. A simple trinomial factors to x minus 3, x plus 2. And something interesting happens here because now we notice that the x minus 3's divide out. That was actually the entire reason we were getting 0 over 0. So now I have the limit as x approaches 3 of x times x plus 2, which is no longer in indeterminate form. I can sub in x equals 3 into that, and I get 3 times 3 plus 2, which is 15. If you want to check that and make sure it was right, try subbing in some numbers close to 3 here, and you should find that you get an answer close to 15. Now, I know what you're thinking. You're thinking, well, you just designed that question, so they divided out. If they didn't divide out, this wouldn't have worked. And you're absolutely correct. I did design it so they divide out, and it wouldn't work if they didn't divide out. But what we're going to learn when we look at calculus is that coincidence always happens. There's a reason it happens. And the reason being is that there is a limit that exists in the questions we look at because the slope of the tangent exists, therefore the limit exists. So this isn't just a designed for a limit homework question. When we do real calculus, these coincidences, they always happen. That's kind of interesting too. Well, I think it's interesting. Okay, for the next example, another limit in indeterminate form. If you sub in h equals 0, you will clearly get root 3 minus root 3, 0 over 0. So we need a different strategy. And these are common to see these type as well. What we can do actually here is called rationalizing the numerator. You've probably been seeing rationalizing the denominator before. It's where you take something like 1 over root 3 and you multiply by root 3 over root 3 so that the denominator becomes a rational number. Okay. It's a little more difficult when you have something like 1 over root 3 take away 1. How do you rationalize that? Well, you multiply by what's called the conjugate, which is root 3 plus 1 over root 3 plus 1. The same strategy works here. We're going to multiply by what's called the conjugate, which is root 3 plus h plus root 3. And then, of course, you have to multiply the denominator by the same amount. Otherwise, you're breaking the rules. Okay? So, there we have it. Now, let's see why this works. Let's see why it rationalizes the numerator. So what you end up doing is you end up multiplying a square root by itself. Just like you multiplied root 3 by root 3. Oh, I'm sorry, that shouldn't have been. That was a mistake, by the way. That shouldn't be 9. That should be 3. When you multiply root 3 by root 3, you get 3, root 9, which is just 3. The same thing happens when you multiply root 3 plus h times root 3 plus h. You get 3 plus h. The next term you get is root 3. I won't write this every time, but I will for this one. Root 3 times root 3 plus h. You can combine those into one root or not. It doesn't actually matter. Because look what's going to happen. I'm using FOIL here, by the way. When I multiply negative root 3 by that amount, I get negative root 3 times root 3 plus h. And you can see that these terms are actually going to cancel out. And then finally, root 3 times root 3 is 3, and I get minus 3. And so I've rationalized this denominator because these terms end up subtracting out. Okay, it's kind of like a difference of squares. When you multiply x minus 3 times x plus 3, you get x squared minus 9. The minus 3x and the plus 3x cancel out. Now the denominator, I'm not even going to bother really doing any multiplication. I'm just going to write h times root 3 plus h plus root 3. Now, why am I not bothering expanding that? Because just from doing enough of these, I realize I don't need to do that. It's going to work out. If it works out, it's going to. So look at the numerator. Look what happens. I have 3 plus h minus 3. Well, the 3 and the 3 cancel out. Subtract out, I should say. I don't like saying cancel. You should explain why something's disappearing. Is it dividing out? Is it subtracting out? In this case, it's subtracting out. And you're left with just h divided by h times 3, all this stuff here. Okay, now, speaking of canceling, the h's divide out. Okay, and that's pretty significant because that is actually going to be the step that makes this limit no longer in indeterminate form. And by that, I mean that I am now allowed to sub in h equals 0 and I will get an answer. I sub in h equals 0 and I get 1 over root 3 plus root 3 or 1 over 2 root 3 for the answer. Notice I'm keeping the limit as h approaches 0 all the way through until I finally substitute h equals 0, and now the limit is equal to this amount. There's no limit as h equals 0, approaches 0 once the h disappears. Again, I know what you're thinking. You're thinking, oh, this was designed nicely. It just so happened that these numbers, it all happened to work out that when you multiply by the conjugate, the 3 subtracted out and you're left with just the h. Yeah, but that's what happens in real calculus problems. In fact, you're probably starting to see this already looking like an equation for a slope of a tangent, which it actually is. But if you don't see that yet, don't worry about it. We still got some more examples to try. So from that last example, you should have a pretty good idea how to start this next one. It looks very similar, and it does require the same strategy, multiplying by the conjugate. 1 plus 4x plus the square root of 1 minus x. And of course, I have to do that on the bottom as well. Okay, when I do that, the limit as x approaches 0. Okay, I'm going to start with the numerator. Okay, root 1, you multiply a square root by itself, you just get whatever is inside the square root. And then I have a weird term here. I have this square root times the positive root, subtract the same 2 roots. So those inside terms in FOIL, they're going to subtract out. The first one will be this multiplied by this, and the second one will be this multiplied by this, the negative. So I don't have to worry about that anymore, but I do multiply root 1 minus x times itself to just give me 1 minus x. Remember, you need those brackets there. Be careful with that. Okay, and then on the denominator, I don't do any work. I just write it out. And there you have it. Now look at what happens when we simplify the numerator. Okay, the 1's subtract out. Okay, I get 4x plus x, I get 5x. Just like so. And again, the x's now are going to divide out, and that's really the key step in this one. I get 5, all divided by the square root of 1 plus 4x plus the square root of 1 minus x. And that is something that is no longer in indeterminate form. You can sub in x equals 0. You get 5 over the square root of 1, which is just 1, plus 1, you get 5/2. Done. Okay, last example. Limit as x approaches 0 of this messy looking fraction here. Again, a very common limit to see when you're working with slopes of tangents or instantaneous rate of change. Notice, always check, can you just sub in x equals 0? No, you can't. You get 4 divided by 2. 2 minus 2 is 0 over 0. So it is, in fact, indeterminate. I kind of like almost seeing that on someone's page when I'm looking at their work, because I know that they did check and make sure that that wasn't a possibility. So what do we do here? Well, this is a mess. It's not even simplified. And when I say it's not simplified, there's a fraction in a fraction, and you never need more than one fraction in an algebraic statement. You can always combine fractions. So let's try that and see if it works. Spoiler alert, it will work. So I'm going to combine the two numbers on top using a common denominator. I get 4 over 2 plus x, subtract, okay, 2 times 2 plus x over 2 plus x. All of that is still over x. All right, well, going from there, I can now combine the top. So I get 4. I'm going to expand here as well. So I get 4 subtract 4 minus 2x all over 2 plus x. All of that is over x. Next, from there, 4 minus 4 is 0. So I get negative 2x, all divided by 2 plus x. And rather than thinking about this as a fraction symbol now, I might just think about it as a division symbol. It's just divided by x. From there, of course, dividing by x is the same as just multiplying by 1 over x. Like that. And now look at these two x's. They're going to divide out, which is kind of the key step here. You're going to get the limit as x approaches 0 of negative 2 divided by 2 plus x. That is no longer indeterminate. You can sub in x equals 0 and you get negative 2 over 2, which is equal to negative 1. And there we go. So to summarize, the ways in which you can evaluate limits are by simply substituting the value in. Okay, if you can do that, you go ahead and do that. In fact, you always usually finish a limit question like that. Perhaps realizing that there's no way the limit could exist. Factoring, which is really just simplifying, to be honest. I mean, this is an unsimplified expression. Yours x minus 3 can be divided out. Rationalizing the numerator, we did 2 examples like that. Or you could rationalize the denominator. So there are limit questions where rationalizing the denominator works. And finally, like finding a common denominator and simplifying, really just simplifying again. I mean, nobody wants to see this. You can always simplify it into something simpler. And in this case, that something similar is no longer indeterminate. those are the main methods. There's one other method that we might look at later. I think I'm going to hold off for now and just have you guys practice some of these. Okay, thanks.